1000. So there is a G+4 structure RCC building you are seeing on the screen, and this building I have taken from one of the previous literature. Just I will show the literature. So this is the literature from which this building is has been modeled, and this is the data. These are the different loads given on the building, and these are loads first of all in SAP 2000. After the model creation, these loads have been defined and then it is assigned. And this building is located in seismic zone 4, and it is resting on a medium soil. So this is the data given. Then we'll perform the pushover analysis for this particular structure. Now see, pushover analysis actually this to be performed in 2 stages. First analysis is dead load nonlinear analysis, and second stage analysis is a pushover analysis. So that is first of all run dead load nonlinear case. Then at the end of dead load nonlinear case, whatever the stiffness of the structure, that stiffness of the structure will be the beginning stiffness from the next pushover analysis. So therefore it is called as a 2-stage analysis. Okay. Now first of all, in the load case, for the first stage, that is dead load nonlinear case, so the case is required to define here. So therefore first is define load case. Okay, now already dead load case is there, but what is the type? It is linear case, linear static is there. So actually it should be a non-linear. So therefore do modification in this, do modification. Then just change the name for the convenience. It is a non-linear dead load non-linear, right? Okay, then here, so these are the 2 types of the, these are the 2 types, that is analysis type. Either we can perform dead load linear or non-linear. Now we are interested in the non-linear. So therefore go for second option. Okay, non-linear. Then next is that now in this table only the dead load has come, but apart from the dead load already on the model, the different other superimposed loads have been assigned. So these superimposed load has to become in this particular table. So which are those? Just click on the drop down list. First is we have applied a brick load external wall. So just add. The next is brick wall internal, add this. Next is parapet brick wall, just add this. The next is dead load order is there. Now EQX, EQY, these are not the loads, these are type of the analysis. Then floor finish, okay, weight of the flooring. So add this. Then next is now live load. Now as per IS 1893, we have to apply a reduction factor for live load as a 0.25. 0.25. Then add this. Reduction is only for live load. Next is also live roof. Reduction is 25%, 0.25. Then lastly, it is a roof treatment. There is no reduction, so it is 100%. Okay, just add this. Okay, so these are the different loads we have added in the dead load nonlinear case. Okay, so this is the information to be filled in this particular case. Say okay. Now the name has been changed as a dead load nonlinear. Okay, then we will define the next load case as a pushover load case. Now we'll perform, since this is a 3D building, we'll perform pushover analysis in global X direction and global Y direction. Okay, now before to, okay, first of all, define the load case. So add a new load case, add new load case. Okay, now first is, it is a push X. Okay, this is a push X direction load case. It is a static nonlinear. Okay, it is a static nonlinear. Okay, now as it is, I mentioned earlier also, this is a second stage analysis. So therefore, here initial condition, go for second option, continue from state at the end of nonlinear case. It means that first of all, dead load nonlinear case will run, and here at the end of this case, whatever the stiffness will be the beginning stiffness for the stage 2. So it is a very essentially click on this particular option. Okay. Then here, now in this table, these different load patterns are there. So these load patterns, what is the meaning? So what is a pushover analysis? Pushover analysis theory, more describe, it is clearly described in detail in ATC 40, 1996 document. So in that, so the structure, pushover analysis is nothing but the structure is subjected to lateral load. Okay, lateral load in one direction until it fails. So there is a progressive failures of the different elements. So it is the load is applied with an incremental loading intensity. Okay, so the element which is weaker, it may be beam or column, so that element will fail first. Then further increase of the load, then second element it will fail, then third element. So in this progressive failures of the structure, we come to know from the pushover analysis, and which is the weakest one, weakest element. So that also we can identify from the pushover analysis. So therefore pushover analysis is a very simple and type of the analysis, and from that we can identify which element need to retrofit. Okay, we need to strengthen. Okay, so for existing building, for strengthening purpose, this particular method is very, very important, very, very useful. So in the load pattern, so in the SAP 2000, there are three options are there for pushing the structure. First is apply a load pattern, apply the load pattern. Second is acceleration generated forces. Okay, just apply the acceleration, that is software automatically apply the acceleration, and because of the acceleration, some lateral forces will be induced. So this is a second option. And third option is the mode shape. Okay, so if the building, that is building to be pushed by the shape of the mode, that is first mode is a parabolic mostly. So apply this thing, the lateral force in the shape of the parabolic, that is shape of the first mode. That is the third option. So in this case, we'll go for the second option, that is acceleration generated lateral force. Why this option? It is not a specific reason. That is why we have selected this. We can select anything, but the third option, that is a mode shape. So that option should be applied if the structure is the first mode dominated structure. First mode dominated structure means the mass participation in the structure is more than 90% in the fundamental mode in that particular direction. If this is the case, then go for the third option. Okay, so in general, for other type of other type of the mass participation that is less than 90%, then the second option is also a reasonable choice. So we have selected second. Then scale factor is equals to 1. Sometimes this scale factor is required to put a minus also. Okay, so when to put it is required to put a minus. For example, finally at the end of once the analysis is complete, we'll get the pushover curve like this. We'll get the pushover curve like this. Sometimes we'll get the pushover curves something in the reverse direction in this way. Okay, same pattern but in the reverse way. So if we get the pushover curve in this direction, okay, this curve is also this thing. It is a correct curve. It shows a response or performance of the structure. Okay, but we are always familiar to see any graph in this fashion. Okay, so suppose we obtain a graph pushover curve like this, then to make the pattern of the pushover curve in this way, like this, then you just change the scale factor to -1. Then you will get the in this way. Okay, so right now we'll keep as a +1, and let me see whether we are getting pushover curve of this type or this type. Okay, then add this. Then second, so now here apply this thing, load applications. So click on modify. Click on modify. Now here there are two important options. Options are there. First is load application. Either it is a force controlled or it is a displacement controlled. These are the two types of the analysis. First, force control analysis is useful up to linear stage, up to yielding point, because after yielding, the structure loses its resisting capacity. Okay, so therefore, without that is beyond yield point, there is no significant rise in the force capacity or the force value. So therefore, force controlled method is applicable up to the for the linear stage only, okay, up to yielding point. But actually this pushover analysis or pushover analysis or time history analysis, or in short, performance based design. So in the performance design is a new design philosophy. In this performance based design, to study that particular philosophy, so there are two methods, pushover analysis and time history analysis, and actually these are the non-linear analysis. So we are very much interested to know the structural behavior in the nonlinear stage. So that is what is the ductility, then beyond this thing, what is the energy carrying capacity. So all these parameters are also important beyond the nonlinear stage, beyond the yield point. So therefore, always the analysis should be a displacement control, because after yield point, okay, so resisting capacity reduces, but further the structure can carry the whatever the displacement applied. So therefore, it must be a displacement control. So go for second option, displacement control. So that is perform based design. In short, it is nothing but a displacement analysis, displacement control analysis, displacement based analysis. Then controlled displacement. Controlled displacement, again use conjugate displacement and use monitor displacement. Now we are monitoring the displacement. This is displacement based method. So we will monitor the second, that is use monitored displacement. Okay, now load to a monitor displacement value. So here the structure will be pushed on one side for a distance, that is the structure will be pushed on one side like this. So for a distance, this distance is equals to this much. So in the SAP 2000, 0.544, this gives a default value. Okay, so it gives a default value, and but the user has a choice. Okay, so this value actually is editable. We can edit this particular value. So sometimes this particular displacement, whatever this top displacement, is actually calculated and structure is pushed up to that displacement. So therefore, that is called as a target displacement. That is called a target displacement. Now in ATC40 also there is an equation given to calculate the target displacement. So user, they can use that particular value equation and estimate the target displacement, calculate the target displacement, and then put that value into this particular box. Okay. Otherwise, you accept this particular default value. So it is actually roughly it is 4% of the height. This is given by 4% of the height. It is given. So it is that is a default this thing. So in this case, we'll just check how much it is. The height of the structure, just will check. 1 minute. So it is a cancel. Okay. Now our height of the structure is how much? It is 13.6. Okay, so 13.6. So 4% of this. 4%, 0.04 of 13.6. Okay, so it is 4% of the height. It is correct. So we are correct. So go for define, again load case, then add new load case. Just repeat the procedure. It is a push X. It is push X. Then it is static non-linear. It should be continued at the end of one minute. Is something we did mistake. This is a non-linear. Then add the load pattern. Brick internal, add this. Then brick parapet, add this. Then the floor finish, add this. Then this is add. Then live load floor, it is to be a live load floor, it is a 0.25. Add this live load roof should be again 0.25. Modify this, and lastly it is a, yes, so it is add this. Okay, so this is a dead load nonlinear case. Okay, then we'll define the pushover case. So then add new this thing. So it is push X. It is a push X. So it is a static nonlinear. It is to be continued at the end of dead load nonlinear. So load pattern we have selected as a acceleration. This thing. One more point I will explain here itself. Now there are to perform the pushover analysis, again there are three options are there. So it is a nonlinear. Okay, see, these are the geometry, about this is about the geometric nonlinearity part. So since pushover analysis, it is a nonlinear analysis. So we have to assign, it is required to assign the nonlinearity to the model. Nonlinear to the model. So nonlinearity are two types. Either first is called as a material nonlinearity, and number two is called as a geometric nonlinearity. So geometric nonlinearity means P delta effect. So in seismic analysis, geometric nonlinearity is nothing but P delta option, P delta analysis. So whether into this pushover analysis you want the result including P delta effect or not. So first is none. Okay, then suppose we have decided yes, P delta effect also will consider. Then again there are two options, P delta and P delta plus large displacement. So among these, which option to be selected? So that is normally P delta and P delta plus large displacement. These are just two methods for solving the equilibrium equations in the software. Okay, so in the case of P delta option, the stiffness matrix is generated at the beginning of the analysis. Okay, and same stiffness matrix is used for the complete P delta, P delta analysis. So that is a P delta. So therefore analysis completes in short time. So it is computationally efficient. While a second option, P delta plus large displacement, in this case, the stiffness matrix gets generated at the beginning of each step, and then it updates. Okay, in the next step, again, there is a revision of the stiffness matrix. And then that the software uses that particular stiffness matrix within that step only. When it enters into next step, then again it generates it updates the new stiffness matrix. So therefore it takes a time. So therefore it is computationally expensive, this particular third option, P delta plus large deformations. Normally, if the building is subjected to vertical acceleration, or suppose the structure is subjected to ground motion in oblique direction, okay, if something abnormal case is there, then go for the third option, P delta plus large deformations. But in the normal condition, second this thing also is suitable. It is P delta. Then in the load, this thing that is, then we'll go for the bottom column, load application. Okay, so it is a displacement controlled. Then second, it use monitor displacement, and here this is 0.544. How it comes? This value, it is a default value in SAP 2000. Total height, it's 4%. So default value it is given. And now we are defining the pushover in X direction, that is U1 direction. This is correct. And this is at joint 6. At joint 6, what it means that it is a monitored displacement. Very great meaning to this monitor displacement. While pushing the structure, the software monitors the displacement. Okay, keep monitoring continuous displacement, and it is not monitoring at all nodes. It is monitoring displacement at one node only, which is that node number 6. Where it is somewhere here. I will show afterwards. Okay, so it is always at the top. conveniently it choose 1 points, but it is at the top floor. Okay, and it monitor the displacement and give the result pushover curve, that is load versus deformation. So that is with respect to that particular point, deformation of that point, right from first to up to the end of the analysis. So that is a point number 6. In this case, this is a point number 6. I will show that point also afterwards. Okay, so this much is to be complete in this. Then okay, then go for next. That is a result saved. Result saved. Okay. Now next is, there are two options. Whether the pushover results we required only of the final state, or we required what are the different steps also, multi-step. So go for second. Go for second. And how many number of steps you required? So minimum, say we required 100. So it is editable. So we can take any value. So but minimum will take as a 25. Then say okay. Okay. Now this is in this way. And third option is also there, nonlinear parameter. Okay, nonlinear parameter here, some nonlinear to that is after all pushover load case, there is a program. Okay, and to solve the program, there is a numerical integration is also there, and the integration parameters are there. So numerical method uses some parameters. So these are the parameters you are seeing here. Okay, so initially don't make any changes in this parameter. Let it be whatever the default value. Okay, when to choose make the changes in these particular values, sometimes what happens, the pushover case will not complete up to 100%. Okay, so the program stuck at a particular point, which is called as a non-convergence. So whenever there is a non-convergence, or whenever the program stuck at a particular the stages, and because of that we will not get the 100% result, complete results. So in that case, then there are different options are there. So first option is you just minimize the monitor displacement. Now monitor displacement is how much we have kept, it is 0.5, that is 4% of the height. So first is you reduce that particular monitor displacement, this thing 0.5 to say 0.4 something, again run the analysis. If suppose again 100% case is not run, then second option, still you reduce the monitor displacement and again try. Again it is not possible, that is then come to this particular dialog box and make changes in this particular nonlinear parameters. Okay, so this is a third this thing. After reducing monitor displacement, again not possible, then come here and again run the analysis, then definitely you will get a pushover curve. Okay, so initially don't make any changes in this. Okay, so in this way, this is push X case we have defined. In the similar way, we'll define the push Y case. Okay, so need not necessarily new load case, whatever the push X case, will add the copy of this. Add the copy of this, and for the Y direction, whatever the necessary changes, you just make it. So name of the case as a push Y. Okay, it is a push Y. So it is everything will be same. Here only change, what is change? It is in the UY direction. Only changes UY direction, modify this, right? Then in the first one, that is load application, you just change this. So instead of U1, it will be equal to U2. It will be U2. Okay, monitor point will be same. This is 4% of the height. Okay, so in this way, this is a push Y direction. Okay, now pushover load case we have defined in global X and Y direction. Now we will start the analysis, but before that, see, pushover analysis or time history analysis, these are the nonlinear analysis. Nonlinear analysis. Now to run or to perform nonlinear analysis in the software, whatever this structural element, these beams or these columns, it is required to assign the nonlinear properties. It is assigned to it is required to assign the nonlinear properties. So now nonlinear properties are two. First is called as a material nonlinearity, and number two is called as a geometric nonlinearity. So geometric nonlinearity is nothing but P delta. It is nothing but P delta. So already we have opted the selected that particular option. So that is about geometric nonlinearity. Then about the material nonlinearity, in this there are two options. Regarding material nonlinearity, there are two options. Okay, first option is that whatever this beam, okay, to define the material nonlinearity to this beam, either we can assign the nonlinearity for complete length of the beam. Okay, if we do like that, then it is called as a distributed plasticity approach. It is called as a distributed plasticity approach. Okay, this is the one way. And second, instead of that, suppose this is a beam, the material nonlinearity is assigned to a specific zone only, here and here only. So end zone, only end zone assign the material nonlinearity. That is the second option. If we do this option, that is material nonlinearity defined at the end, then this is called as a lumped plasticity approach. Literature or research from various researchers, study from various researchers says that is either you go for the material, that is lumped plasticity approach, or distributed plasticity approach. The results are very closely matching. Okay, now the simple approach is this. Simple approach is this, that is called as a lumped plasticity approach. Now in this case, we'll choose this particular option, that is lumped plasticity approach. Okay, now in the sense, to define the nonlinearity at the end, here and here. Now the question is that why at the ends only? Why at the ends only? The reason is that, first reason, if we see the different various photographs of damages of the building different elements in the past earthquake, it has been found that most of the columns and the beams have been fade at the ends only. That is the first reason. Second reason is that the frame subjected to lateral loading. Then what is a bending moment diagram of a beam? The bending moment diagram of the beam is like this. For all beams, the bending moment diagram is like this. That is, the flexural stresses are maximum near to the ends. Okay. Similarly, what is the bending moment diagram for the column? So the bending moment diagram for the column is like this. Okay. So here also the bending moment or the flexural stresses are maximum at the ends only. These are the bending moment diagrams under lateral loading, like a earthquake loading. So therefore, the end zones are very important. There is a high concentration of the flexural and shear stresses. So therefore, if the failure is there, that failure will be at the end only. So in the lumped plasticity approach, therefore, plasticity nonlinearity is defined by assigning a plastic hinges. Okay, but so assign a plastic hinge here and assign the plastic hinge here. Okay, now these plastic hinges to assign at the end, again there are two options. One is user can estimate the properties of these particular hinges. Now which properties? First of all, moment curvature property, and then moment rotation relationship, and from that estimate the hinge properties, and then assign the hinge here and here. So such types of the hinges are called as a user defined hinges. And second is that in SAP 2000, so there are some ready-made hinges. There are some ready-made flexural hinges. So you just choose that particular hinge and assign properly at the end. Okay, and these hinges are called as Ato hinges. So again, study from the various researchers says that either you use a user-defined hinge or Ato hinge. The results are very closely matching. And in the Ato hinge case, the user need not necessarily to do any calculation regarding the properties of the hinges. Within a very few minutes, we can assign the nonlinearity. Otherwise, user-defined hinges to assign it, so it will take a very, very long time. Okay, so therefore, do not go for the user-defined hinges. If your study is a specific about the hinge property, okay, then go for that type of the option. Suppose the sections are composite sections. Okay, RCC column plus I section, some composite columns are there. Then in that case, such the hinges for such a sections are not available in the SAP 2000. So in that case, you have to go for the user defined, the hinges. Now in this case, since this building is a conventional type, so therefore we'll go for the Ato hinge, whatever the hinges given in the SAP 2000. Okay. Now first of all, we'll assign the hinges to all beams. Hinges all the beams. Okay. Then first of all, select all beams. Select all beams. So the command is select, then properties, then frame section. Okay. So these are the different beams we have defined separately. So select all. So beam exterior, beam interior, beam terrace exterior, and beam terrace interior. Okay, so these hinges select and close. Now in the 3D model also we can see all the beams have been selected. Okay, then go for here, assign. Okay, see the carefully this thing, assign, then assign frame and hinges. Assign frame hinges command. Okay. Now define the relative distances. Okay, so for a beam or column, this is a beam. So first hinge will be here. Okay, so this end will be 0 and this end will be equal to 1. Okay, so we will assign the hinge somewhere here. So that is relative distance equal to say 0.1. And second, this is equals to 0.9. Second hinge we will assign here. So first is at relative distance 0.1, then click on add hinge. Okay, then so this is a code, ASA 41 2017. This is a code, American code is there, and from in that code there are different tables giving the parameters for the estimation of the properties of the hinges. So in the SAP, these particular parameters it is inbuilt, and therefore you code keep as it is, and here just select the type of the member. Now this is a concrete beam. It is a concrete beam flexure. Concrete beam flexure. Okay, then define the degree of freedom of that particular hinge. So remember, for a beam, always it is M3, because deformation of the beam is how much? How the deformation is? The beam deformed like this. Okay, so this deformation is with respect to a axis perpendicular to this, that is M3 axis. Therefore, always for a beam it is M3 degree of freedom. Then in the in the calculation of the hinge properties, shear value is required at that location. We are assigning hinge at the end. So what is the shear value? So there are two options: case combination, okay, that is, and second is a user value. Okay, user value. Now we will this thing will give the option to that case combination. That is, already we have defined a dead load nonlinear case. Okay, and by using dead load, under the dead load nonlinear case, whatever the shear forces are coming at the end, so let the program use the same shear forces value to estimate the hinge properties. That is the first. And second is user value. Suppose you have some shear force values are there calculated from different formulas based on your study. Then also you can go for the second option. Okay. Then next option, transverse reinforcement is confirming. So always, if the building is a ductile resisting building, it is a ductile type of the frame is there. That is what is called as a special moment resisting frame. Okay, so that is ductility detailing reinforcement has been done. Then in that case, go for this particular option. Transverse reinforcement is confirming. If it is an old building, if model is an old building where ductility provisions in the reinforcement detailing has not done, then in that case, just uncheck this. But since our building is a new building and it is a special moment resting frame, therefore go for the second. Okay, and these are some default options are there. Keep as it is. Okay, so these are the options taken from the ASA 41. So keep as it is, take as it is. Okay. Okay, so hinge at 0.1. have been defined. Then second location is 0.9. Then add this hinge. Okay, so it is the same, this in parameter comes, whatever we have defined for 0.1. So just for OK. Okay, just for OK, and then apply and say OK. Okay, now in the 3D view also we can see all the beams at the ends. See this at the ends, hinges have been defined. Okay, so these are the numbers. Different hinge have different numbers. 33H1, 33H2. Okay, these are the numbers are there. Okay, then we'll assign for the columns. So in the same way, so assign frame and in this hinges. Okay, now for the column, first is relative distance equal to 0.1, add hinge. Okay, so ASC 41. Now select here as a column, concrete column, yes. Now degree of freedom. So degree of freedom for the column is a PM2M3. Column is designed for axial load plus movement in 2 directions. So keep this as a degree of a freedom equals to this. Right. Then again same, that is P values, axial force value. So in the both gravity plus, for gravity and gravity plus lateral will keep the same, that is dead load nonlinear and dead load nonlinear, keep as it is. Then other parameters are from ASC 41, keep as it is. Okay, so it is, do not change in this. So it is okay. Then next is a 0.9 second hinge, add this. So the same properties as a 0.1 location. Okay, so it is okay. Now somewhere it is a mistake. So again we'll assign. So it is a select, yes, properties, frame section, then column, select. Okay, then assign frame, then hinges. First is 0.1, add the hinge. So it is a concrete column, it is a PM2M3. Then it is a keep as it is. Then okay, second 0.9. Then this add this hinge. This is the second hinge at a 0.9 relative distance. Okay. Okay, and here at the bottom for the beam case also and for column case also, always keep default as a replace existing hinge assigned with a specific. So sometimes what happens, previously is you have assigned some hinges. Okay, so when you assign the new hinge, automatically it replaces the previous hinge. So mostly you keep the same as the replace existing hinge. Then apply and okay. Apply and okay. This is closed. Okay, now see all the hinges to the columns have been also assigned. Now we have assigned the hinges to the columns as well as to the beams. Okay, now this is part is over. Then we have assigned the nonlinearity, material nonlinearity to the columns as well as for the beams. Okay, now we will hide this particular, the hinges. How to hide this? You just click here, show undeformed shape. Okay, now hinges are there. Okay, but it is just hide. Okay. Now we will see the generated properties, hinge properties. Okay, so how to see that is already it has been assigned, but what actually it is assigned, what are the properties of the hinges, that first of all see. So go for define section property, and here it is hinge property. Okay, and here one option is there, show generated, show hinge details. Sorry. So it is define section property, hinge property. Cancel this. Define section property and hinge properties. Section property, hinge properties. Here option is, second option is that, okay, here show generated properties. click on this. So when we click on this, okay, so these have been hinges have been assigned. Okay, now do you want to see any hinge properties? Do you want to see any hinge properties? Okay, so let me check. Okay, so that is moment M3. These are the hinge property to the M3 in the sense these are for the beams. Okay, select anyone. Okay, select anyone and just modify this. Okay, so what is the type? It is a deformation controlled hinge. It is, then we'll modify again. This is the hinge property name is there. Then modify show hinge properties. Okay, now these are the hinge properties of this. Okay, now this is a moment rotation curve, and these are the values, moment and rotation. Okay, so this is the property of this particular hinge. So it is a case specific. If we take the another hinge, so these values are something different, because at that particular section of the beam, it depends on the cross section dimension, what is the reinforcement, what is the grade of the concrete, what is the detailing of the lateral reinforcement, all that it depends. So this is a case properties. So in this way, we can see the hinge properties. Similarly, for the column also we'll see anyone. So for example, this, we'll select this and go for modified show properties. So this is for a column 43s. Okay, so it is a PM2 M3 hinge. So this thing modify angle. So this is automatically this thing. So this is a this is moment rotation data. Then second, this is interaction curve also it shows. Okay, so this is the interaction curve under PMM action. Okay, so this is the interaction curve. Again, this is a case specific. This is for this particular, the hinge, that is 443 H2 hinge. Okay, it differs from the column to column. Okay, so in this way, we can see the generated property of the hinge. Okay, now we'll start the pushover analysis. Now, before that, this thing, while defining the pushover case, I said that the monitor displacement at joint number 6, where the joint number 6 is that, just we'll see where the point number 6. So click on this thing, display option, and here the labels is there. So you just check these labels, then apply and OK. Apply and OK. Okay, now where the point number 6? Now this is a point number 6. Okay, so that is this point. This is a point number 6. So software monitor the displacement right from initial stage of the pushover analysis up to the end. Okay, now we'll start the analysis. Run. Now it will take a little bit time, but as compared to time history analysis, the time taken required for the pushover analysis is less. Therefore, pushover analysis is a very simple method for the analysis. And this particular method is applicable if it is a first mode dominator structure. If in the structure, if any irregularities are there and the torsion is the dominant effect, then in that case, instead of performing pushover analysis, we have to go for the nonlinear dynamic analysis, nonlinear time history analysis. So pushover analysis, even though it is simple, but it has its own limitations also. So here, this is the analysis this thing status. So it is now 8 steps are have been saved. Okay. Now the analysis completes. Now we'll see the different results. Okay, different results. So before that, one warning has also comes. Warning has also come. So the warning indicate that the analysis is not completed. Analysis is not completed. There are some the errors. The program found some errors in this. Now again we this thing unlock the model, and we can reduce the the monitor displacement, and again rerun the analysis, and again you will find there is no error. Okay, but even though in this case we'll see the pushover curve, and then we'll decide whether the this rerun analysis is required or what. So first of all, see the pushover curve. So go for display and static pushover. Okay, now the curve is there. So it is showing the linear part, also it is showing the non-linear part, and it is but it is a reverse curve. It has come a reverse curve for push X also, and also push Y is also, it is a reverse curve. In both it is showing the reverse curve, and so we don't actually the results are okay, but we are not habitual to see the reverse curve. So therefore what we'll do, we'll make the change as we'll unlock the model. Then we'll do one thing. So here in static pushover case, this particular case, modify to this as a -1. Okay, modify this, and we'll reduce slightly the monitor displacement, because there are some errors also found. So instead of 0.544, we'll apply 0.4, then say okay. So this is we did in the X direction. Same correction we'll do in the Y direction. Again here also the curve is a reverse curve. This modified, and monitor displacement will reduce to as a 0.4. Okay, again we'll run the analysis. No, it is showing here. Now that is now this push Y case is going on. Out of the push X, so it first of all completes push X case, and then we start for the push Y case. So 79% analysis has been completed. Okay. Again, there is some warning error. Okay, so there are 42 warnings are there. So again, it is required to reduce some monitor displacement, again rerun. Okay, again some this thing warning comes, then make the changes in the nonlinear the parameters. Okay, now again we'll see the pushover curve and this thing result. Okay, so we'll see what the results we are getting. So first we'll see, always you see the static pushover curve. So you will get here static pushover case, pushover curve. Now it is in the right direction. It is from left towards right. Okay, so this is in the push Y case, and this is in the push X case. Okay, so the curves are we are getting. So, and actually it is showing the deformation up to 360 or near to 0.4. That is, we have this thing. So that is, it is showing the complete capacity of the structure. This is also called as a capacity of the structure. Therefore, it is called as a capacity curve in X and Y direction. So I think, as per my opinion, it is not necessary to rerun the analysis, even though the warning is there. So that is in the program. There is some non-convergence. Therefore, it has come. Warning has come. But here, by seeing the pushover analysis, it is showing complete capacity. So not necessary to go for the this thing, rerun the analysis. So we'll see the other results. So from the pushover analysis, which results to be observed, that is first of all, we require the pushover curves, capacity curve in x and y direction. So these are the curves in this way, and these curves we can see in the tabular forms also. So go here, table, and this is display table. Okay, display table. So display table, and the table we can export into the Excel also. So we'll get this table into Excel. Okay, what this curve is? So this is a, okay, so this is which case? It is pushover X case. Okay, so this is step numbers 0, 1, 2, 3, 4 steps is there. Displacement, these are the displacement. Okay, monitor displacement at point number 6, and these are the forces, base shear. Okay, so this is the curve is like this, the curve is like this. Okay, so these are the displacement when the structure is pushed by step number 1. What is the displacement? Displacement equal to this much meter, and how much force is 465. Step number 2, 110, 1621. Then increasing step, base shear is goes on increasing. Okay, so this is a displacement versus force. So in this direction there is a displacement, in this direction there is a force, base force, and these are the results are there. And what is this? These are the hinges developed at each step. Okay, and these are the different performance criteria, A to B, B to C. What is the meaning of this? Just I will explain. So meaning of this is that in ATC 40 or FEMA 356, performance behavior is given. Okay, so that is the curve is like this, from this to this, then write this, then from this to. Now these are the names are there. This is A, point A, this is point B, this is point B, and this is C. These points are there. Okay, then now B to C, it is divided into, this segment is divided into first, and this is what a movement versus rotation curve, behavior of the hinge, right? Okay, then it is a this is one, then second point is here, and third point is here. Okay, so these are called as this is called as a immediate occupancy, I2O, immediate occupancy. This is called as a life safety. Okay, and this is called as, third is called as a collapse prevention. These three are known as the performance points. These are called as a performance points as per FEMA 356. Okay, now here, now B to C, see, B to C, from B to C, how many hinges have been formed? 0 here. Then from C to D, from C to D point is here, D point is here. Okay, then A to B, first is A to B, that is from this to this, that is in the linear stage. How many hinges are there? 400 hinges are there. 400 hinges, that is how many total hinges we have assigned. Just for your remembrance, we have assigned some hinges to the beams at the ends and some hinges to the columns. So how many number of columns? So for each column we have assigned 2. So those many number of hinges to the columns and those many number of hinges to the beams. How many total hinges? 400 hinges we have assigned. Out of 400, in the first step, okay, in the first step, almost 398 hinges are in this particular range, that is in the linear range. Deformation in that hinge is a linear. Okay, in the second step, in the second stage, okay, 348 hinges are in the linear stage, while as 52 hinges are in the next range. What is this next range? B to C, are in between, from B to C range is there. Okay, when we go further, say hinge step number 12, now 194 hinges are in the first, that is A to B. 194 hinges are there. 202 are hinges in between, from B to C are there. Okay, and 4 hinges are there, which crosses the ultimate limit point. This is a yield point. and this is the C point. So C to hinge, there are four hinges are there, which crosses the ultimate point. C point is there. So this is a completely failed. This is the completely failed. 202, these hinges have crossed the yield point, the deformation or the rotation at the yield point. They have crossed the yield point. Okay. Then, for example, hinge number 20, step number 20. See, still 168 hinges are in the linear stage. 182 hinges have been crossed the yield stage, and 50 hinges have crossed the ultimate. That is, these are completely failed. That is in the step number 20. Okay, so that is in each step, 1, 2, 3, 4, how the hinges have been developed in each model, in each element, and how many number of hinges and what is their state, whether they are in the linear stage, whether they have some of the hinges have crossed the yield stage, and some hinges will cross in the ultimate stage. So all this information will get from this particular table. Okay, now this particular table, see, all this table you have to read with respect to this particular graph. Then you will understand what is this notation A, B, C, D. And this graph you will find in FEMA 356 2000 document, or it is ATC 40 document, or in many research paper you will find this particular, the hinge behavior of the structure. Hinge behavior of the, this is a hinge behavior of the flexural hinge. Of the flung, it is called as a deformation controlled hinge. Its behavior is like this. Okay, so you must know what is A, what is B, what is C, and what is D point. And then after studying this, then come to this particular table, you will understand this particular table more effectively. So first of all, study this particular table, this particular graph. Okay, so this is about the table. I will close this table. So this is in the about the push X and push Y. So this is the push Y direction. Okay, first thing. Then second, again, then click here. Click here. Now second is a ATC 40 capacity spectrum. Capacity spectrum. Okay, so there is one method given in ATC 40, what is called as a capacity spectrum method. And from capacity spectrum method, we will get one point, what is called as a performance point. This is called as a performance point. So what is a performance point? It is intersection. It is intersection of the two curves, capacity spectrum and demand curve. Wherever there is an intersection, that is called as a performance point. Okay, that is called a performance point. So to know the performance point, that is when the demand curve is implemented on the structure. So demand curve in the sense response spectrum curve, when it is imposed on that particular structure, then structure, how much is the displacement, maximum displacement occurs in the structure. So the performance point shows that particular displacements. Okay, or stage at the structure state at that particular the level of the demand curve. So that information will get from the performance point. Okay, so in short, I will explain in other way also what is significance of the performance point. For example, here now we will on this given structure, we will implement, we will apply, okay, we will impose the response spectrum from IS 1893. Okay, so how to impose this? Okay, now here this particular, okay, so this particular response spectrum is from the American code, right? American code. We can make the change, or we can use the same spectrum, but we'll change the property of it. How to change the property of this? Okay, see, click here, modify show pattern, modify show pattern. Okay, so here we can change it is as a IS 1893. Okay, then IS 1893. Okay, now first is, this is plot axis. Now, whatever this capacity spectrum, so it's usually it is x-axis is a spectral displacement and y-axis is a spectral acceleration. So let it be. So keep as it is. Now here, user define. Okay, now as per IS, for IS 1893, what are the value for CA and CV? Just substitute this value. Now in IS 1893, there are two earthquake levels have been defined. First level is called as a design basis earthquake level, DB level, and number two is called as MC level, that is maximum considered earthquake level. Okay, right. So for a maximum considered earthquake level, what are the value of CA and CV? So for that, just I will show you a one literature. Okay, so here one literature paper is there. Okay, so you just see this particular paper. You will find this paper on a Google also, and very nicely this Rahul, Mr. Gentleman, explain this pushover case very simple way. You will understand very better way. Okay, so this is the flexural hinge behavior. Okay, so I am explaining this particular graph previously. So this graph you will find in this literature also. Okay, so here these are the values. Okay, in short I will explain in short time. See, so these are the values. So on comparison, CA is equals to Z by 2. This is for which level? DB level. This is for a design basis earthquake. So CA value should be equal to Z by 2. Now our building is situated in seismic zone 4. So what is Z value? 0.24 divided by 2. 0.24 divided. So it is a 0.12 value. So CA value will be equal to 0.12. Okay, and what is CV value? What is CV value? Okay, CV value will be equal to again it is Z by 2. It is Z by 2, 1.36 Z by 2, or it is 1.67 Z by 2 respectively for soil type number 1. This is for soil type number 1, type number 2, and type number 3. Okay, now ours is a type number 2. It is medium soil, so it is type number 2. So what is the value? 1.36 Z by 2. Okay, 1.36 Z by 2. So for design basis earthquake, what is the value? 1.36 into 0.12. So what is the answer? It is 1.36 multiplied by 0.12. So how much value? 0.16. So 0.16 is the value of CV for design basis earthquake. For design basis earthquake. So it is a 0.16. Okay, now these are the value for DB level of earthquake. Okay, for DB level earthquake, and for MC level of earthquake, you just double it. Okay, so it will be 0.24 and this will be 0.32. Okay, so now we will impose DB level of earthquake and just update one in the here, update the plot. Update the plot and say okay. Update the plot. Okay. Okay. So what it is shows that, just I will check these parameters. See point how much? 0.12 and CV value is a 0.16. 0.16. Okay. So it is update plot. Update the plot and say okay. A parameter name must be entered. ISS. Okay, here. It is a IS 1893. Update the plot and say okay. Duplicate parameter name. Okay, something is wrong. Okay, we'll take the new new one and give the name as IS 1893. And here will this thing, it is a 0.12 and 0.16. Okay. Then update the plot and say okay. Duplicate parameter name. Which parameter name? Duplicate parameter name. I think already we have defined anything. Yes. IS 1893 already we have defined it. We'll make the changes. Yes. IS 1893 already defined. Okay. Already it is defined. So therefore, so here we will give the name something IS 1893 2016. So it is 0.12 and 0.16. Okay. Then update the plot and okay. Yes, now it is. So there is some this thing already name is known. So therefore, when the dB level of earthquake is imposed on the structure, okay, so it is not giving any performance point. Not giving any performance point. What it means that the structure is weak in y direction. That is, even though it is not taking the dB level of earthquake also. Okay, and MC level earthquake is the next part. Okay, MC level earthquake means still the seismic intensity is double of this. So the structure is not taking dB level earthquake. It means that obviously it will not take the MC level of the earthquake. So therefore structure is very weak. Okay. Second, this is in the y direction. Suppose we'll check in the x direction also. Okay. Again, we'll this thing for IS 1893. Again, new parameter. Say IS 1893 2016. Okay. Change the parameter as 0.12 and 0.16. Then update the plot. Okay. No, something is not that. It is a IS 1893. We'll give the name only IS 1. Say IS. There is some problem with the name. Then these are the two parameters CSCV. Update the plot and say okay. Okay. Now in the x direction it is taking. Okay. Now what is the performance point? So it is getting performance point in the sense in x direction the structure is very strong. So it is taking the dB level of earthquake very safely. Okay, then see. So what is the effective time period? Effective time period is 0.595. 595 is there. What is the use of this value? Just remember 0.595. So a performance point. Now go to table, see table and display table. So what is the value? 0.59. So 0.59 value is something in the somewhere here. 0.59 is in between 3 and 4. Okay, so this is a T effective. So let me take as the step number 4. We'll assume that the performance point a stage achieved at step number 4. Now step number 4, we'll see the deform shape and we'll see how many hinges have been developed at the stage number 4. Okay, done. Okay, so this is say okay. Now go in this particular 3D view and go for display deform shape, and here it is a push X, and step number how much? Step number 4. Here step number 4. Apply and okay now. Okay, how many hinges have been developed? So most of we are seeing green colored hinges. Okay, we'll see this thing also. So it is display, show deform shape, push X, stage number 4. Okay. So see, so the hinges have been developed. Okay, and most of the hinges are in the green color. So green color in the sense it is after B. So this is showing this thing. This is the status bar. Okay, so what is the state? B in the sense B, it crosses B point. That is yield point have been crossed. Now B to C. So B to C, it is a B to C, it is a immediate occupancy stage. Okay, so just I will for the this is very important. See, the graph is like this. It is like this. So this is A point is here, and this is B point. This is B point, and this is C point. Just that in the Rahul this thing, this graph is also there. Okay, so B to C. Okay, so this is a first step. First color is a IO limit. So that means, so this green color indicate that the hinges are developed. These are in the immediate occupancy state. So that is in the X direction, the structure is very safely is taking the dB level of earthquake. Now in the X direction itself, we will impose the MC level of earthquake. Let we see. We'll increase the intensity to double. What will happen? So here again go for display static pushover curve. Okay, ATC 40. Okay, ATC 40. Now here it is IS type and modify this. Modify. Now this will be double. It will be 24 now, and this is 32. It is 32. Update the plot. Okay. Okay. Now how much again? When the MC level of earthquake is there, again T effective is the same, 0.568. Okay, 0.568. That is nearly the same as the previous T effective value. That is the dB level of earthquake. That means the structure even is taking MC level of earthquake. So structure is very safe in the X direction. Okay, and but found to be weak in the Y direction. Only for one time we'll see Y direction capacity. We did some mistake around. So we just change here as a Y direction. No, actually we did some mistake. We did some mistake. So this is this is MC level earthquake. No, update the plot. Okay, see. And so this is in Y direction. It is Y direction. And just check the modifier, this thing. Now see, what are the parameters? 0.24 and 0.32 parameters are. That is MC level of earthquake is there. MC level of earthquake, update the plot. Okay. Okay. So see, that is we did mistake while defining some parameter or somewhere in the giving the case name this thing. It is found that in Y direction also, when MC level of earthquake as well as dB level of earthquake, the performance point it is getting. So performance point getting in the sense the structure is capable of resisting dB level of earthquake as well as MC level of earthquake. So in this way, so this is the use of ATC 40 capacity spectrum. Okay, so that is whatever the imposed earthquake, whether it is taking or not, capable or not, that we can see from the capacity spectrum method. So this is the second this thing option. Then other some this thing FEMA 356 coefficient, then FEMA 456 equivalent linearization. Okay, so that is one some other types of the curves also we get from this. So this is a bilinear curve. This is called as a bilinear curve. Some of this study we required to convert our pushover curve into bilinear. So that is from this to this one segment, and second is the from this to this segment. So bilinear to convert into bilinear curve. So we'll get from this particular option. Okay, so this is a about a pushover. Again, one more point that hinge status. Okay, so that is we can see. So display hinge result. When you click on a hinge result, so one this thing. So select any one hinge. So this is in the which state it is? A to B. That is, it is in the immediate occupancy stage. So click on any hinge and then just change the position of status bar. Again, see here, it is still this hinges from A to B, immediate occupancy. What is level? It is immediate occupancy stage. So actually the structure is very strong. Therefore, it is the hinge. And now for this, we will see. Okay, again, it is a hinge. It is in the show backbone curve at this curve. Okay. Again, it is in the hinge is in the linear range only. Okay, so in this way, sometimes if the complete failure is there, so that also we can see. Now here something. Okay, so fortunately here some failure is also there. Okay, so it is a Ato hinge is there. Okay, so here, see. So this is a now still it is a hinge status is A to B, but color is changed, I think. So color is changed. That is, it is immediate occupancy. Here you just see. And now it is B to, it moved to B to C. That is from immediate occupancy to life safety. The color shows that it enters into life safety range. So like this, we can see all these are complete 400 hinges are there, and we can see their status from this. Then we can see the total deform shape pushover. How many cases we have? Total, it is a 20 steps have been completed. Apply and okay. So at the end of this thing, okay, now this is a C to D. So some hinges, whatever you are seeing, these colors. Okay, so these colors, all these hinges are crossing C point. Crossing C point means crossing the ultimate point. So this is the complete failure. Complete failure. Okay, so if we want to see the progressive failure, which is a weaker one, so go for deform shape and start to see the results right from the first. Results from the first. Okay. And now this is the first step. And then here, go for the second step. You just click on. So these many hinges have been formed. Okay, but all are in the linear range. Then see, again, another in some other elements, hinges have been formed. Hinges formed in other locations. Hinges formed in other locations. Some then previous again are the immediate occupancy stage. Then go for the next. Then go for the next. Go for the next. Click on this. All the green color, it means that still are very safe hinges. Now see here. Now just previous case. So very closely see here the first hinge here and internal samir here. This now changes color to this color. Now crosses the ultimate stage. So these are the locations of the weaker locations are these. Okay, so this is identify such locations we can identify, and then suitably we can make the changes. That is, since this is a new building, already it is designed for seismic action, but after performing pushover analysis, we come to next here, these are the locations still need to improve. So we can make the changes in the design and make these particular locations to be stronger. This is a performance-based design. By seeing the performance, by running after the performing the pushover analysis, identify this